Hi, today we're very happy to have Alex Maloney from McGill. Alex, please take it away.
Good. So thanks for the opportunity to speak today. It's always great to be back in Chicago. I mean, I guess that's what I would usually say. But it'll be great to be back in Chicago at some point in the future. Yeah, so today, excuse me. So today I'm going to talk about a paper that came out a few months ago with Edward Witten. And there was a very closely related paper that came out on the same day by Nima, our host, along with some of his co-authors. And so, I was warning Nima earlier that my internet connection today seemed like it was a little unstable. But if it goes out, that's no problem because Nima could just take over and give the rest of the talk. So don't worry about that. Good. And also, maybe before I even begin, let me just start by noting that I really want to try and give a sort of informal Blackboard style talk. One of the things that I've discovered in our new, era of physics in the time of coronavirus is that it's even more important when giving an online talk to try and keep things as interactive as possible. So for that reason, I want you to think about this as a Blackboard talk. Feel free to interrupt. I'll be disappointed if people don't interrupt and ask questions. And so, yes, and please also feel free to give me feedback if something is unclear, or if you'd like me to elaborate on something, I'd be very, very happy to do so. Good, so let me just begin with a very general overview. So my goal today is to try and address the following question, which is there some sense in which gravity, by which I mean semi-classical theories of gravity, like Einstein gravity, emerges from some sort of averaging procedure? And before even trying to begin to answer this question, I'd like to emphasize that there are really two different things that I could mean when I say gravity emerges from an averaging procedure. One thing that I could mean is that some sort of gravitational dynamics will emerge when you average over some large number of configurations in some given theory. And this sort of way that gravity emerges from an averaging process is really rather familiar to many people who've thought about gravity. This is the sort of thing that would arise in, for example, statistical mechanics, where we have some sort of coarse graining procedure. And indeed, in the sort of modern picture of black hole quantum mechanics, if you have many individual quantum states, which could be regarded as the microstates of a black hole, then each individual microstate might not have a semi-classical gravitational description, but when one coarse grains over these many states, it has a gravitational description in terms of some semi-classical black hole geometry. And so there's already a sense in which just the standard picture of black hole microstates would tell us that a semi-classical gravitational description will emerge upon some sort of averaging procedure. Okay. But when I ask whether gravity emerges from averaging, this is not the sort of averaging that I am talking about. So this first type of averaging is not what I am talking about. Instead, what I am talking about is an ensemble average over many different theories. So here, what I'm talking about is a theory of gravity arising when one studies not just a single quantum mechanical theory, but rather many quantum mechanical theories in some ensemble, where if one averages over this ensemble in the correct way, then some sort of gravitational dynamics emerges. Okay. So there actually is some precedent for this sort of gravity emerging from an ensemble average in the literature. So for example, in 2D gravity, there is a particular model of gravity known as Jakob-Teitelbaum gravity, where this is reasonably well established by Saad, Schenker, and Stanford. And in this case, this is a two-dimensional theory of gravity which via the ADS CFT correspondence, you would expect to be dual to a one-dimensional quantum system, that is to say a quantum mechanics theory. And indeed, there is a particular ensemble average over Hermitian matrices, which could be thought of as the Hamiltonians of a one-dimensional quantum mechanical system, which has the property that when one averages over this ensemble of random Hermitian matrices, one gets the Jakob-Teitelbaum theory of gravity. Of course, this is an extraordinarily simple theory of gravity. It has no local degrees of freedom. It is, such a simple theory of gravity that one can really compute the path integral exactly and rewrite it as a theory of random matrices. And so the natural question is whether there are more complicated, richer theories of gravity for which this same fact is true, that gravity can be thought of as emerging from some sort of ensemble average. And the next case that one might want to consider is that of three-dimensional gravity. In particular, three-dimensional gravity is a theory that has been studied for many years. It turns out that if one studies three-dimensional gravity in anti-de Sitter space very carefully, it has some signatures which one can interpret as being hallmarks of a theory that is describing not an individual quantum mechanical theory, but an ensemble average over many quantum theories. In particular, there was a calculation that I did in 2007 with Witten, where we computed the partition function of 3D quantum gravity in anti-de Sitter space. In particular, we computed the thermal partition function of the theory, which encodes the spectrum of the theory. And we discovered that this thermal partition function is not the thermal partition function of a quantum mechanical system because it has several pathologies. And in particular, one of the pathologies that it has is that it has what looks like a continuous spectrum. And gravity in anti-de Sitter space is a little bit like physics in a box. One would expect it to have a discrete spectrum. And so the fact that the spectrum is continuous was regarded as evidence that three-dimensional gravity in anti-de Sitter space does not exist as some sort of quantum mechanical theory. However, in retrospect, we could instead interpret the fact that there is a continuous spectrum perhaps as a suggestion that 3D gravity in ADS is not dual to a single quantum mechanical theory, but rather to an ensemble average of many quantum mechanical theories. In particular, each individual conformal quantum mechanical theory in this ensemble, which we think of as a two-dimensional conformal field theory, would have a nice discrete spectrum, but when we average over many of them, we get a continuous spectrum. In the same way,
could
yes,
I interrupt
please.
for a second?
Mm-hmm.
It seems that you're saying two slightly different things here, and I'd like to make sure I understand the distinction.
Please.
So on one point, you're saying this continuous spectrum suggests that in the duality, there should be something more complicated, perhaps an average. But you are also saying that having a continuous spectrum is a pathology of 3D gravity in ADS by itself without reference to any duality, because it's like being in a box. So
the way, maybe I can try and address that. So each individual, so the picture that I would advocate that I think has a reasonable likelihood of being true is that pure three-dimensional gravity in ADS is a theory which is given by an average over all 2D conformal field theories. And with a particular measure, actually, that I'll speculate on if you give me the opportunity to later.
And with a particular central charge determined?
Yeah, so for example, depending on what is fixed on the right-hand side, that tells you what to fix on the left-hand side. So for example, if you fix the ADS radius in Planck units of the theory of gravity, that corresponds to fixing the central charge of the family of CFTs that we're going to average over. Now, each individual element of that ensemble is a particular two-dimensional conformal field theory, which, formally speaking, could be interpreted as a theory of quantum gravity in ADS. I mean, one of the points of the ADS-CFT correspondence is that any CFT has a stress tensor. The stress tensor correlation functions can be interpreted as the graviton scattering amplitudes of some theory of gravity in ADS, and the various CFT axioms correspond to various sort of expected nice properties of those gravitational scattering amplitudes. But any individual instance of the ensemble is not dual to pure three-dimensional gravity in ADS. Okay? That is to say, the theory that you get by quantizing general relativity with appropriate asymptotically ADS boundary conditions. Okay? So I think the natural guess might be that pure Einstein gravity in ADS is an average over all two-dimensional conformal field theories. That's a speculation. We can talk more about that. I mean, Nima invited me to a discussion session afterwards the talk, when that would be a great time to talk about that rampant and unfounded speculation. Good. Did I answer your question, Jeff? Or well,
I guess
go ahead.
If I just forget about ADS-CFT, would you say that you're saying that 3D gravity in ADS has a continuous spectrum, right?
I'm saying that the quantization of general relativity in anti-de Sitter space has a continuous spectrum.
And just as a theory of gravity in ADS, do you find that pathological?
Yeah. I mean, an average over, well, it depends. I mean, an average over a set of quantum systems is not a quantum mechanical system with a Hamiltonian and a Hilbert space. Okay. I mean, maybe we can, yeah.
Okay.
Okay. I have a lot more speculations I can make, but yeah.
Okay.
Okay. Maybe I can draw an analogy here, which is how I secretly think about this subject, although I haven't admitted it during this talk yet, which is that I'm really quite motivated by the analogy with ensemble averaging in condensed matter physics and statistical mechanics. So for example, when one studies spin glasses, very frequently you're studying a very complicated, a spin glass is a perfectly nice quantum mechanical system, but it's a very complicated one. And in that case, the ensemble averaging procedure that one uses to study spin glasses is really, it's not saying that an individual chunk of a spin glass is not a quantum mechanical system. Instead, what it's saying is that the process of ensemble averaging is a technical simplification, which allows us to extract a sort of, effective calculational theory, an effective theory that governs the dynamics of the theory, to a very good approximation. And so in the same sense that any individual chunk of spin glass is very well approximated by the ensemble average, where you average overall coupling constants, one would expect that a typical element of this ensemble of all two-dimensional conformal field theories would be very well approximated by the ensemble average. Okay. This is a typical feature of chaotic theories. Chaotic theories which exhibit, for example, self-averaging or something like that, have the property that each individual instance of the ensemble is more or less representative of the whole. Okay. And the natural speculation is that this is the sense in which we should think of a theory like semi-classical Einstein gravity in ADS as one of these theories that is an extraordinarily accurate approximation to each individual theory in this ensemble, but one which is not exactly accurate. In the same sense that if I took a very large n by n matrix and studied the statistics of its eigenvalues, it's very accurately approximated by random matrix theory, but it doesn't have a continuous eigenvalue spectrum, right?
Yeah, I was going to say you could talk about nuclear physics rather than
exactly. You could also talk about nuclear physics, where a giant nucleus could be very well approximated by some random matrix or something like that. But that doesn't mean that your nucleus is not a good quantum mechanical system. In this analogy, each individual nucleus is an honest-to-God quantum theory of gravity with a Hamiltonian and a Hilbert space, and general relativity is the effective theory that arises when you perform this ensemble averaging procedure. Good. So my goal here is to try and find a framework or a set of examples where all of these very fancy words can be made precise. Okay. So
can I just ask
please.
Can I just ask a basic question to get
Yeah. Please.
When you say 3D gravity and ADS, does that mean fluctuations of the metric about the ADS metric?
Yeah. So
okay.
Absolutely.
Are they linearized or just?
Absolutely. So
okay.
when I was making the statement about 3D gravity having a continuous spectrum, there's a vast body of literature on the subject that I don't necessarily want to take too much time to summarize. One of the quirks of three-dimensional gravity is that there are no propagating gravity waves, so there's no linearized degrees of freedom, much like Chern-Simons theory in 3 dimensions. There are no linearized degrees of freedom. Nevertheless, the theory does have non-trivial dynamics. It has black hole solutions. It has edge modes, which are just like a Chern-Simons system, like a quantum Hall system has edge modes associated with the presence of a boundary. 3-dimensional gravity also has perturbative degrees of freedom, which you can think of as edge modes. So now edge gravitons, as opposed to the sort of edge modes that you get in a quantum Hall system. But there's a whole long story there that I don't necessarily want to go in to describe. But when I say that it has a continuous spectrum, I'm including not just the linearized fluctuations, but also a non-perturbative calculation where I'm computing a path integral via sum over geometries.
Okay, thanks.
And that sort of, yes, please, but let me, and that sort of sum over geometries is exactly what will arise later on in this talk. Good. Yeah, but there was a question.
Are the graviton edge modes responsible for the continuous spectrum? Like, what is the physical excitation that gives rise to the continuous spectrum?
The continuous spectrum arises from a sum over geometries. Those geometries, loosely speaking, can be thought of as black holes. I have a very specific calculation in mind, but that continuum is really the continuum of black hole states. Yeah. It's much more non-trivial than the edge modes, which are completely governed by the symmetry structure of the theory. Good question. Yeah. When I talk about this continuous part of the spectrum, the part which we should loosely speaking think of being analogous to random matrices and having this interesting chaotic dynamics, we're really thinking about black hole states. Although the model that I'm going to describe today is a bit simpler than a theory of gravity, it's a bit simpler than 3-dimensional general relativity ADS for reasons that I'll describe. Good. Okay. So the ADS CFT correspondence tells us that any 3-dimensional theory of gravity is equivalent to a 2-dimensional conformal field theory. So if one wants to develop a theory where 3-dimensional gravity emerges as an average over quantum mechanical systems, what we really need to do is to develop a theory of random conformal field theories. In the same way that JT gravity was dual to a theory of random matrices, 3D gravity should be dual to a theory of random conformal field theories. However, if you think about it for a second, random conformal field theory is going to be a much more complicated beast than random matrix theory. To begin, let's start by thinking about the data that defines a 2D CFT. So the data that defines a 2D CFT is first a spectrum. That is to say, a list of operator dimensions and spins for all of the primary states in the theory, along with a list of coupling constants. So in particular, a list of OPE coefficients, which roughly speaking are the cubic coupling constants of the theory. Now, for a matrix is just described by its eigenvalue spectrum, right? That's the only basis-independent information in a matrix. But in a two-dimensional conformal field theory, we have not just the spectrum, but also the OPE coefficients. And what we would really like to do is find some way of averaging over this data. In the same way that when we study a random matrix theory, we really are averaging over eigenvalue distributions with some measure. So to do this, there are really three things we need to do. So the first thing that we need to do is find the allowed values of this data. So find the allowed values of the spectrum and the OPE coefficients. Then we're going to need to determine a probability distribution on this allowed data. And finally, we're going to need to compute something. We're going to compute an average and then ask whether it takes the form of some sort of gravitational system. Okay. Now, this is, at first sight, a very complicated task. So, for example, step one in this process has a name. It's called the Conformal Bootstrap problem, right? The Conformal Bootstrap problem is the problem of finding all allowed conformal field theories. That is to say, finding the set of data that define the set of allowed values of the data that define a conformal field theory. And of course, the Conformal Bootstrap problem is a very long and difficult problem. You know, it's a time-honored, difficult problem. You know, it's almost tantamount to the problem of solving non-perturbative quantum field theory.
Sorry, Alex,
Yes.
Shouldn't you be able to average, if this program were really to be useful, you should be able to average for conformal field theories without first solving all conformal field theories, right?
No.
In the spin glass, you don't first solve for the exact spectrum of the spin glass and then average over that data.
Well, that's indeed. Okay, good. You could imagine an alternate procedure where you just start with, so we would, however, like to only include values of the spectrum and the coupling constants that are consistent with unitarity.
Fine, but you know, for instance, if we had a class of conformal field theories that was described by some set of local fields and some kind of Lagrangian, we could average over that data without first solving for the exact spectrum of the interaction field.
Fair enough. I mean, there are many different ways you can proceed. In fact, one of the things that you could certainly imagine doing is just performing this average without trying to first solve the conformal bootstrap problem. I mean,
yeah.
Okay, let's put it this way. I'm presenting a straw horse. Is that the right phrase? Yeah, I'm presenting a straw man. I'm presenting a straw man and beating a dead horse. Right. So I'm presenting the straw man argument.
Right. You intend to go around it. I understand.
Intending to circumvent
where you've already accomplished one.
Exactly. Exactly. Yeah. So okay, this is a straw man argument. That's good. I like that. I have a straw man riding a dead horse, something like that. Good. But of course, you could imagine other ways of proceeding. But yes. But carrying out this procedure is really quite difficult. So instead, what I would like to do is consider the simplest family of theories And in particular, what I want to do is the thing that we always do in physics, which is if I have a problem that's too hard to solve, I keep adding symmetries until I can solve it. Okay. So in particular, I'm here trying to average over spaces of conformal field theories. So I'm going to start adding symmetries to my conformal field theory until the problem is easy enough to solve. Now, for two-dimensional conformal field theories, when we add symmetries, what we really mean to do is to enhance the chiral algebra of the theory. So add chiral operators to the theory. So what I want to do is consider conformal field theories with chiral algebras that are as big and as simple as possible. So in particular, I'm going to consider theories with a chiral algebra, an algebra of chiral operators, that is just a bunch of U1s. And I'll call the number of U1s capital D. And I want the number of U1s to be as big as possible. And it turns out that the largest value it can be, consistent with unitarity, is equal to the central charge. So I want to consider this special family of conformal field theories. And it turns out that for the special family of highly symmetric conformal field theories, in fact, one can solve the conformal bootstrap problem, because these are CFTs of D free bosons. And if you want the theory to have a discrete spectrum, they're going to be D free bosons on a torus of D dimensions. So this is a theory of maps from a two-dimensional world sheet into a D-dimensional torus, which you could think of as real D-dimensional space modded out by some lattice. Here, now, hopefully it should be apparent why I've called the number of free bosons D, because in the language of string theory, this would be a string world sheet theory of a theory in D space-time dimensions. Now, so the space of conformal field theories is then the space of possible free boson theories, which very loosely speaking is characterized by your choice of this lattice here, although there are some subtleties. And it turns out that the space of such conformal field theories is well understood. There is a modulized space, which is simply Narain's moduli space of conformal field theories. So that's the space of such conformal field theories. It's finite dimensional. It has dimension D squared. And in particular, it's a homogeneous space. And so because of that, there is a unique invariant measure on this space, and hence a unique invariant probability distribution.
Invariant under what, and why is that important for this problem?
So invariant under the ODD symmetries of free boson compactifications. So strictly speaking, so the space of such conformal field theories is described by a signature D comma D lattice, which is acted on by ODD. We'll get to all of this in a bit more detail later on if I have time. The fact that the metric is invariant simply means that it's easy to write down, but the reason why it's the correct probability distribution is that the measure on this moduli space is the one that's induced by the Zamolodchikov metric. So for each, so this is a continuous moduli space of conformal field theories. Motion in moduli space is generated by a marginal operator in the theory. The two-point function of these marginal operators defines a natural metric on this space of conformal field theories, which is Zamolodchikov's metric. And perhaps not surprisingly, the homogeneous metric that is invariant under the signature D comma D rotations of these lattices is the same as this Zamolodchikov metric. That one can check explicitly. So this is, I would say, from both of those points of view, the natural measure and hence the natural probability distribution on this space.
But so I guess I was just trying to understand if we were forced to average with that. I mean, I understand.
You're certainly not forced. You're certainly not forced to.
Okay. Right. I'm trying to understand which parts of the rules are made up and which parts of them are kind of derivable from.
Let's say there is a unique natural probability distribution. Clay is welcome to be as unnatural as he likes. Yes, so there certainly are other probability distributions that one could choose. The interesting thing, or one interesting thing about this invariant probability distribution is that we can compute the average of absolutely everything. Okay? And in particular, when I say we can compute the average of absolutely everything, let me tell you what I mean.
Well, Alex,
yes,
I have a different question than Clay. I like the measure and not bothered by it.
No. I mean, I'm just making fun of Clay in order to get him to stop asking questions.
He can take it.
I know he can take it.
My question is, these moduli spaces are continuously connected to other moduli spaces, like orbifold moduli
Yeah,
spaces.
these break.
Is there a physical principle that would tell you when you're doing this average that you shouldn't make a little detour that is just an infinitesimal marginal perturbation of the theory?
Yeah. Well, good.
So subspaces.
Right. So for example, so the C=1 case is the one that I remember well, where like you have the the horizontal axis is like the axis of just free bosons, but then at some particular value of the radius, probably the self-dual one, although maybe not.
No, it's not the self-dual.
It's not. It's like √2 or something like that. You can detour off, and you can get to these S1 mod Z2 orbifolds. When you do that, however, you lose this enhanced chiral algebra.
Right.
So what I've done here is I've chosen a problem where I don't have to worry about that. Obviously, if I wanted to average over all C=1, for example, conformal field theories, then I would need to include all of these orbifold theories as well. The problem is that I don't know how to compute that average for arbitrary central charge. I suppose I do know how to compute it for central charge 1, although I don't happen to remember the answer.
I thought your things were very divergent at D=1.
No, well, okay. You can actually, for C=1, it turns out you can regulate. You actually can get a finite answer by doing a zeta function regularization. It actually turns out to be 0 in some sense. Don't ask me why.
I guess I agree it's mathematically more well-defined if you do what you're doing. I'm just wondering if there's some principle.
Clearly the right thing to do would be to average over all conformal field theories, but that's too hard. Okay. I'm not smart enough to do that. And so, for example, one thing that you might want to do is find a more limited class of theories where one could perform this average, but that's still bigger than this Narain moduli space that I've described. So, for example, we could try including orbifolds. That would be the next place to look. I have some speculative words I could say, but for now, I'll just say that I have defined the problem where I average only over theories with this ginormous chiral algebra so that I don't need to worry about that. So for example, for these S1 mod Z2 orbifolds, it's only at this particular value of the radius of the S1 that you happen to get this enhanced chiral algebra. Yeah. But I do think that averaging over all orbifolds, so, there's lots of things you could imagine doing. One question that I've asked myself as well, you could take n copies of your favorite conformal field theory, which has an Sn symmetry. And instead of doing a symmetric product orbifold, you could average over all permutation orbifolds, over all subgroups of Sn and see what you get. I don't know what the answer is. I suspect that there's interesting things to say there, but I'm not going to say them today. Good.
Okay.
Great. But the reason why, and in fact, our motivation for choosing this particular family of conformal field theories was not that I know the moduli space of such CFTs. I know lots of CFT moduli spaces. The motivation was that I know how to average things over this moduli space. And in particular, what I know how to average is everything. So for example, it is believed that all of the data of a conformal field theory is packaged into the all genus partition functions of the theory. And I can compute the average of the all genus partition function, where I have here an arbitrary Riemann surface. So I can compute the average of the all genus partition function, not just the torus partition function, but the partition function on any surface averaged over this moduli space. And I can ask whether it has a gravitational interpretation. Okay. And so in order to ask whether it has a gravitational interpretation, let's begin by thinking about what such a gravitational interpretation would look like.
Alex, I thought in your paper you claimed that you could not do this average, but rather you could only do it for certain genus that depended on D.
Okay, I am
very high genus.
Okay, I am, for the sake, again, I have the disadvantage of giving a talk to people who have read my paper. So there is a subtlety, which is that the sum that I am about to write down in some cases diverges. But let me talk about the unsubtlety before I talk about the subtlety.
All right.
Good.
Well, yeah.
Good. So in order to, good. So let's begin by asking, what sort of answer would I expect for a gravitational theory? Well, let's begin by thinking about a gravitational theory in a semi-classical limit. So in a semi-classical limit, you would expect your the partition function of some gravitational theory to be a sum of classical saddle points, each of which is weighted by 1 over h bar times the action of that classical saddle point. And here, 1 over h bar is going to be the inverse coupling constant of the theory, which is basically the central charge, which is this parameter that I called d. So this is what you would expect in a semi-classical theory. And then once one starts including quantum effects, you would have a 1-loop term, perhaps a 2-loop term, and so on and so forth. Now, it turns out that when one computes this average, this is exactly the structure of the answer that we get. In particular, you get something that looks like the sum over geometries of some 3-dimensional theory of gravity, along with a classical action and a 1-loop piece. And in fact, although in a general theory of gravity, you would expect all sorts of perturbative corrections to appear here. Indeed, you would expect this to be an asymptotic series rather than a convergent series. It turns out that the structure of this theory is so simple that all of these terms just vanish. And so the theory is 1-loop exact. So the conclusion is that the average over this moduli space of conformal field theories takes the form of a gravitational path integral. So this looks like a gravitational path integral in a theory where we know all of the saddle points, and in particular, I'll draw them for you, and the 1-loop corrections. Of course, a typical quantum theory is not one where you can find all of the classical solutions and compute all of the perturbative corrections around a given saddle point. But this theory that we're studying today is so simple that you can just list all of the classical solutions, and you can compute the all-order perturbative corrections around any given saddle. And you can compute them because it's one loop exact. And as we'll describe later, it's a theory that does not look exactly like general relativity, but instead it looks like the obvious modification to general relativity in 3 dimensions that you would study if you were studying a theory with a bunch of U1 currents rather than a theory with just a stress tensor. So this is sort of the introduction, just setting the overall tone for what I wanted to talk about today. What I'd like to do now is spend a little bit more time talking about this averaging over Narain moduli space and how we compute it, and then talking about this gravitational theory, what these saddle points look like that we're including in the sum over geometries, and how we compute these loop corrections. So, as usual, everyone did exactly what I asked and asked lots of questions. So I may not, I may not have time to get into too much detail, but again, I'm always happy to pause and answer questions. So are there any questions before I continue? No, everything is crystal clear. Good. So let's ask about how we might go about deriving a formula like this one. Good. So what we want to do is try and understand how we might perform an average over the moduli space of free bosons. Okay. So to begin, let's just think about a single free boson. So here, a single free boson is a theory. So that's a theory that has a moduli space. What is the moduli space? Well, again, we want theories with discrete spectra. So it's 3 bosons on a torus, or I should say on a circle, a single free boson on a circle. And the modulus is the radius of that circle. And the action is just the usual action, dx d bar x. Okay. So the moduli space that we're studying then is then the set of all allowed radii. Okay. However, we need to remember that this theory has T-duality. So in fact is invariant under r goes to minus r. So the actual moduli space of conformal field theories is not parameterized by an arbitrary radius, but only by an arbitrary radius up to the T-duality relation that takes r to 1 over r. So you can think of r here as a coordinate on moduli space. And then, as promised, there is a natural metric on this moduli space, which is invariant under this duality relation, which is just dr over r squared. So this is the natural metric on this moduli space. And if we were studying a single free boson, when we think about computing an average over moduli space, what we mean when we compute an average over moduli space is literally an average with respect to this measure. And we would integrate r from 1 to infinity because of this r to 1 over r T-duality symmetry. So what about in higher dimensions? Okay. So for D free bosons, we now have a bunch of such fields. The action, the most general action that you can write down, now includes a bunch of free parameters, not just the compactification radius. And the most efficient way of packaging them is in terms of a target B field and metric that we usually call G and B. So now this moduli space, again, you can think of G and B as a set of coupling constants that define this moduli space of conformal field theories. You can see from this that it's now a dimension D squared moduli space because G and B are symmetric and anti-symmetric D by D matrices respectively. G and B form a nice set of coordinates on the moduli space. But a better way of thinking about this moduli space is to think about it as a homogeneous space. So in particular, you can think about a theory of D-free bosons in terms of a signature D comma D self-dual lattice. D comma D because you have to think about the right movers and the left movers separately. And the space of such lattices is the coset of OD comma D by OD times OD. But we still have the analog of the T-duality symmetries, which are just SODD matrices valued in the integers. Whereas here, in the numerator, we have SODD valued in the reals. An important point here is that if we hadn't modded out by that T-duality symmetry, you would get a space of infinite volume. So this might not be apparent from our simple D equals 1 example, because for D equals 1, the volume of this space is infinite on its own. But it turns out that as you increase D, things get more convergent, and this moduli space has finite volume for all D bigger than 1. And so because of that, it makes sense to think about this as a probability distribution. And now when we talk about an average, literally all we mean is an integral over this moduli space with the natural invariant measure that is associated with this moduli space, thought of as a homogeneous space with SODD symmetry. Good. And in fact, it's not even all that hard to write down explicitly what this invariant metric is in terms of these coordinates on moduli space that I've given you, namely in terms of this metric in B field. Good. So this is the moduli space. Let's now think about what it is we would want to compute. So what we want to do is to compute the partition function of the theory. And what is the partition function? Well, it's going to depend on two things. So let's imagine, for example, computing the partition function on some surface, sigma, which you could take to be a torus, or you could take it to be some more complicated surface, like some higher genus surface.
Could I ask a question quick?
Yes, please.
In this action, are you allowed to add like another term, like an ADX term, just as like a background? Like a linear in DX?
This is the most general action that one could write down, which is consistent with the chiral algebra, the U1 to the D times U1 to the D chiral algebra. Of course, there's many different things that one could add that, you know, if you were to relax the assumption of this chiral algebra, but this is the most general thing that we can add for now.
Okay, thanks.
Was
I also
there
have a quick question.
Mm-hmm.
Yeah. So if we want to think about just the single periodic boson, I can think about that as living on the boundary of some Chern-Simons theory, right?
Okay.
what does this R deformation correspond to in that interpretation? Is that understood?
I'm sure it is. I mean, this is the Lettinger liquid theory, and this is what's referred to as the critical exponent of the Lettinger liquid.
Mm-hmm.
In terms of the, I'm not actually sure I'm sure that there is a simple characterization in terms of.
I think it's just a variation in the boundary condition. Nothing.
Is that right?
Nothing in the bulk. Yeah.
Okay. Yeah. Okay. That sounds right. Okay.
All right.
Good.
Thanks.
Okay. So let's now imagine that we wanted to compute this partition function. So let's imagine. So we're studying a theory of d-free bosons on some Riemann surface, and it's going to depend on where we are in moduli space. Okay. So I'll just write m, little m, as my name for a coordinate on moduli space, so I don't have to keep writing g and b everywhere. And it's going to depend on my Riemann surface. Okay. But it's only going to depend on the Riemann surface through the period matrix of the Riemann surface. Okay. So on a torus, this omega, in fact, let's keep our notation simple and pretend we're thinking about a torus. So on a torus, this would be the usual modular parameter tau of my Riemann surface. So this would be the thing that is trace q to the L0, q bar, L to the 0 bar, that encodes the spectrum of the theory on the torus. Okay. And then there would be an analogous computation that one could do for higher genus Riemann surfaces. But when we compute this for a theory of free bosons, we can take advantage of the fact that it's just that, it's a free theory. So in order to compute the partition function of a free theory, you don't necessarily have to work very hard, because the partition function of a free theory is really divided into two parts. So the first part is a one-loop determinant. So in the present case, it would be the determinant of the kinetic operator for free bosons, or 1 over the square root of the determinant of the kinetic operator for free bosons. And then, because we have many classical solutions which correspond to the winding modes around this torus, we have a sum over classical solutions. So as always, when you have a free theory, the partition function is computed exactly. It's just a one-loop determinant times a sum over classical solutions. And in the present case, it turns out that the only thing that depends on where you are in moduli space is the sum over classical solutions. So here we have the sum over classical solutions, which is known as a theta function. So in particular, when you're studying the theory on a torus, this is a traditional theta function of the sort that you would encounter in a math textbook. And when you study the theory on a higher genus Riemann surface, it's also a kind of theta function. It's what people sometimes call a Siegel theta function, or what we call the Siegel-Narain theta function in our paper. Now, when you're studying the theory on a torus, this can all be written out explicitly. So for example, this one-loop determinant is something that captures the contribution of all of the descendants in the theory under the U1 to the D chiral algebra. Sorry, and I guess this would be to the dth power if we're considering D free bosons. When you're considering the theory on a higher genus Riemann surface, we don't have an explicit expression for this one-loop determinant, but nevertheless, we know that it's going to be independent of where you are in moduli space, and that the only moduli dependence comes from the sum over classical solutions, okay, which is some sort of theta function. So it turns out that such theta functions are much loved by mathematicians. And one of the reasons why, well, I suppose there are many reasons why they're loved by mathematicians. Mathematicians love studying lattices. And one of the reasons why these theta functions are useful is that it turns out to be quite easy, relatively speaking, to integrate them over these moduli spaces. So if you look in the mathematics literature, you'll see a literature, going back many, many decades, going back to Siegel, and in fact, even before Siegel, to the discussion of how one averages these over moduli space. But I'll just summarize by saying that there are formulas that allow one to compute the average of these theta functions over moduli space, and they take the following form. So it turns out that the average over moduli space, that is, say, the integral over this homogeneous space, so then it's going to take the form of this one-loop determinant, which is just going to go along for the ride because it doesn't depend on where you are in moduli space, times something that's known as an Eisenstein series. And so since I was writing down only the formula on the torus above, I'll just write down the analogous formula on the torus here. So this Eisenstein series is a sum. It's a sum over all elements of SL2Z times the imaginary part of tau transformed by this element of SL2Z to an appropriate power. So here, tau is the modular parameter of my torus. So if I think of gamma as a 2x2 matrix, then this is A tau plus B over C tau plus D, where gamma is the 2x2 matrix with elements A, B, C, and D. And this quantity in the parentheses here is what is known as a real analytic Eisenstein series. For those of you who've encountered Eisenstein series in number theory, you've probably encountered what are known as the holomorphic Eisenstein series, which essentially don't have this imaginary part here. So these are rather different beasts, these real analytic Eisenstein series. But nevertheless, they're the quantities that arise when you average these CFT partition functions over this Narain moduli space. Okay. And then there is a similar expression at higher genus. So in particular, the only thing that happens is that this group, so first of all, for higher genus, instead of having a modular parameter tau, this would get replaced by a period matrix, which is now a G by G matrix for a genus G surface. This modular group, SL2Z, would get replaced by an appropriate symplectic group, which is the modular group at higher genus. And we would stick a factor of a determinant in here, because now it would be the determinant of the imaginary part of the modular action on some genus G period matrix. Okay. So this is what in the mathematics literature people call a degree G real analytic Siegel-Eisenstein series. Okay.
Is there a simple way to see that this is a convergent series?
Great question. Right. So, I'm technically speaking out of time, but I'll answer your question anyway, but I won't go into too much detail. So for G equals 1, one way of writing this, so this is a sum over SL2Z, but in fact it's a sum, I didn't mention it, but I wrote it, it's a sum of SL2Z mod Z, which it turns out is uniquely labeled by those integers C and D that live in the on the lower rank, the lower row of that SL2Z matrix. And m tau transformed by gamma. So the imaginary part of gamma tau is the same as the imaginary part of tau divided by c tau plus d squared. And then we're taking that to the d over 2 power. So you can see that if d is sufficiently large, this is going to be convergent. And as someone already mentioned, I guess Jeff already mentioned in the comments, it's convergent only for d bigger than 2. And you can just convince yourself of that pretty easily by noticing that I'm summing over a pair of integers in the denominator here. Okay. So when d is equal to 2, you're going to get something like a harmonic series and a divergence there. Okay.
Alex, I'd like to ask you about d equals 2, but maybe I should wait until.
Good. I mean, I can tell you, yeah, I'm happy to tell you. So it turns out that for d equals 1, so it turns out that if you think of this, so Eisenstein series love being regarded as analytic functions of that parameter and the exponent. They can be defined by analytic continuation for any value of that exponent d. So for example, at d equals 1, actually, there's a regularized version of the answer. It's basically zeta function regularization. The regularized answer turns out to be 0, as in the partition function is 0 for a single free boson when regularized in this way. For d equals 2, however, this analytic continuation has a simple pole, just like the simple pole in the zeta function at s equals 1. And in fact, it's not just like the simple pole in the zeta function at s equals 1. It is the simple pole in the zeta function at s equals 1.
Well, I guess maybe I'm asking about, I don't know if this is the same as zeta function or not, but if you look at the holomorphic version of these Eisenstein series at weight 2, which I think is the analog.
Yeah, these are these quasi-modular forms. Yeah.
Then, yeah, it's not absolutely convergent, but it's conditionally convergent. So there's a way to order the sum.
Great.
And of course, you can't prove the modularity without absolute convergence, but
yeah,
you get, as you know, something that is Mach modular, and then it has a completion. I was wondering an analog of that here, where it's conditionally convergent, and you can order the sum in a way that gives you an answer.
That's a great question. I don't have an answer to that. That's a great question. The way that I've organized it here, this is the difference between real analytic and holomorphic Eisenstein series, is that strictly speaking, this is a sum of positive definite quantities. So reordering is not going to help you. You can see just by this expression here.
Yeah, okay.
So when you have holomorphic sums of this sort, you can get any answer you want by rearranging things.
That's right. So it's not going to. Yeah.
But which is not to say that there's not something interesting that can be done there. I think it may well be the case that there's some sort of quasi-modular object that you could construct, but I don't have anything constructive to say. But that's a good question. Yeah. Good. I'm running short on time, however. So what I'd really like to do is just spend a couple of minutes now talking about the gravitational interpretation of this result. And then maybe we can have a lengthy discussion afterwards for all of the further details. So in particular, the question that we want to ask then is what the bulk gravity theory should look like. So the first thing that we note is that the boundary theory, that is to say the ensemble of CFTs that I'm looking at, have a huge global symmetry group. So in particular, they have a U1 to the 2D global symmetry group. And one of the things we know about ADS CFT is that global symmetries in the boundary become gauge symmetries in the bulk. So we expect that our bulk theory should have an analogous huge U1 to the 2D gauge symmetry. Okay? And of course, if I asked you to write down the simplest possible theory with such a gauge symmetry in 3 dimensions, then you would immediately say, well, it's got to be a 3-dimensional gauge theory. with a U1 to the 2D gauge symmetry. And the simplest thing you could write down is Chern-Simons theory. So here what I've done is I've introduced D gauge fields that I've called A and B, and I've written down U1 to the 2D Chern-Simons theory. Okay. Now, U1 Chern-Simons theory is about the simplest possible theory we could write down because U1, the structure constants vanish, so there's no coupling constants in the theory. And because of that, one can actually perform loop computations in U1 Chern-Simons theory to your heart's content because the theory is one loop exact. Okay. In fact, it turns out that, and this is a bit non-trivial, you can compute the partition function of U1 Chern-Simons theory on, actually, okay, let me step back. So let me just step back and say that the partition function of U1 Chern-Simons theory on any 3-manifold is going to be one loop exact, simply because all of the coupling constants vanish. So this is our guess for what the bulk theory should look like at the perturbative level. This is the part of the bulk theory that captures the perturbative contributions of the theory. But we saw up above that our theory also had something that looked like a sum over geometries, because we had the sum that came from the average of the theta function. And it turns out that this sum has a rather beautiful interpretation. So in particular, let's imagine that if our boundary is some Riemann surface, then the simplest 3-manifold, let's call it Y, whose boundary is that Riemann surface, is just given by the natural thing that you would write down if I said, well, find me some 3-dimensional geometry that fills in a Riemann surface. Okay? So in particular, if I handed you a genus 2 surface like the one that I've drawn here, you would just fill it in the way that I have written here, by just embedding that surface into a 3-dimensional space and then looking at the interior in that 3-dimensional space. That's known as a handle body. And in fact, these handle bodies are precisely classified by the data that I described in my sum above. So for example, for a torus, the handle bodies that fill in a torus, you would draw them like this, are classified by SL2Z mod Z. So how do you think about that? Well, I told you that you can classify elements of this coset SL2Z mod Z by a pair of coprime integers C and D, which were the lower row of that SL2Z matrix. What does that map to in this picture? Well, if you think about this handle body here, so a torus, thought of abstractly, has 2 cycles that are treated completely democratically. But when I draw a handle body here, one of the cycles is contractible in the bulk and all the others are not. So for example, this cycle that I have drawn here is contractible. And if I gave names to the 2 cycles on the boundary, then the general choice of handle body in the bulk would be one where a cycle of the form Cx plus dy is contractible in the bulk. So our conclusion is that the sum over SL2Z should be interpreted as a sum over geometries. And indeed, it turns out, although I didn't dwell on it in too much detail, it turns out that at higher genus, we had this more complicated quantity, this more complicated symplectic group that characterized our sum over our sum. And indeed, that group is precisely the data that characterizes a handle body that fills in a genus G Riemann surface. So the result is that the sum over either SL2Z or SP2G, Z can be interpreted as a sum over bulk geometries that fill in a boundary surface. Finally, for each such handle body, we can compute the Chern-Simons partition function on Y. It's a reasonably straightforward one-loop computation. I say reasonably straightforward because you might think it's completely straightforward because the coupling constants vanish, and in a Chern-Simons theory, there are no local propagating degrees of freedom. It's a little bit subtle because to do the calculation carefully, you need to take into account the fact that there are ghosts. It turns out that the kinetic term in Chern-Simons theory cancels mostly against the corresponding ghost kinetic term. There's a little tiny bit left over when you do that one loop computation. And that little tiny bit is exactly what you need to reproduce this one loop determinant. Okay. And the thing that's rather remarkable is that you can show that this is the case, even though you can't compute it exactly in terms of elementary functions. So even at higher genus, one can actually show that the Chern-Simons partition function calculated at the loop level in U1 Chern-Simons theory on one of these handle bodies exactly equals what we call the perturbative part of our free boson determinant on the boundary. Not entirely surprising, but still nevertheless a bit non-trivial. So our conclusion then, and I apologize for going over time, is that the average over Narain moduli space, the moduli space of free 2D CFTs, takes the form of a gravitational path integral including both a sum over geometries, that is to say a sum over 3 manifolds, and a contribution from perturbations around a given 3 manifold for an exotic theory of gravity but it's a theory of gravity that doesn't look quite like Einstein gravity in the bulk, but rather it looks more like a U1 Chern-Simons theory in the bulk. I think maybe in the interests of time, what I would like to do is just stop here. I do have a lot more that I could say, both about the calculation as well as about the interpretation of this result. But maybe in the interest of time, I'll stop here and then take some questions afterwards. Good.
All right. Let's thank Alex and
thank you.
Let's take maybe 5-minute break, and then people who need to leave can leave, and then
Yes.
we'll stick around for questions.
Good. So yeah, great. Okay. So I'll be back in 5 minutes.
All right, I'll stop recording.
Okay, thanks.
Thanks, Alex.